Today we are going to talk about negative feedback op-amp circuits. And we are going to start by analyzing a circuit using our practical op-amp model. And during that analysis, we are going to measure a few quantities that we haven't really had an opportunity to look at before, because this is the first of our circuits that's actually designed to operate in the linear range. So our circuit of interest will be this guy, where we have our op-amp circuit, and we are going to employ negative feedback. Let me put my power supply voltages here so I don't run into things. We're going to employ negative feedback by connecting our inverting input terminal to our output terminal, like so. Where I'm going to call this resistor R2. Here is where our output voltage is taken, V out. In this particular instance, we are going to be looking at an open circuit output voltage. We are going to ground our non-inverting input terminal. And finally, we are going to apply a resistor here, which I will call R1, at which we will apply our input voltage V in. So this is a negative feedback circuit because our feedback loop is formed from the output node to the inverting input node. Okay. So as we discussed in our last class meeting, for a positive feedback circuit, a portion of the output signal is applied to the input and it's added continually, which is why it pushes the output to reach either VCC plus or VCC minus. So effectively, we're going to have an unstable system because a small change in our input voltage is going to cause a correspondingly large change in our output. A negative feedback amplifier circuit is the exact opposite. A portion of the output signal is subtracted from the input signal, and so we see that we have a very high degree of stability. That high degree of stability we will find comes at a cost of reduced gain. So that's not really a disadvantage here, okay? And I'll explain by what I mean by that as we do our analysis. But if you recall, the open loop gain of these amplifiers is usually extraordinarily large, on the orders of tens to hundreds of thousands, if not higher. In a negative feedback configuration, we get to set the gain of the system by our feedback network, which in this case is these two simple resistors. Okay. So we are going to work this problem numerically. So I'm going to give you the parameters of our network. I'm going to say that R1 is a resistor having a value of 5 kiloohms. R2 is a resistor having a value of 10 kiloohms. And our input voltage in this case will simply be 1 volt. Our op-amp has the following parameters. Rn is equal to 1 mega ohm. And for the sake of argument, let's say that R out is equal to 100 ohms. And finally, our open loop voltage gain, AVOL, is going to be 10 to the 5 or 100,000 volts per volt. So these are the quantities that are given to us. Bradley, were you raising your hand?
I wanted to ask, is the closed loop voltage gain R2 or R1?
We're going to find that out in a little bit. You're very close, but not quite.
Does the open loop
Right, exactly right. So we are modifying the open loop voltage gain by closing the loop here.
So that will be our house.
No, it will for right now, until we learn how to look at the ideal op amp case and why we're able to do that. This is absolutely going to show up. Okay. All right, so let's talk about the quantities that we are going to be looking for, and we're looking for several of them. Okay. So the first quantity that I am interested in is simply the output voltage for this system. Okay. I feel like that's fairly self-explanatory. Our second quantity of interest is going to be AVCL, which is the closed loop voltage gain. So we're going to see how that differs from our open loop voltage gain.
What's the exponent of the gain?
10 to the 5. Our third quantity of interest will be our differential voltage VD. Our fourth quantity of interest will be our input resistance RN. I'm using a lowercase r here because I'm going to explain what I mean by this. Okay, so we are not looking for the input resistance of the op amp because that's given to us. What we're looking for is the input resistance seen by the source that we are applying. Okay, and that's going to have a different value that is going to be shaped by a combination of this feedback network as well as the input resistance of the op amp. Okay, so the expectation here, getting a little bit ahead of myself, is that when we apply negative feedback, what that's going to do is it's going to cause an increase, an effective increase in the input resistance of the op amp itself, meaning that we should see the voltage R1 in parallel with an extraordinarily high resistance, even higher than 1 mega ohm. Okay. That negative feedback is going to cause the inverse effect for the output resistance. So our output resistance of 100 ohms, our expectation here is that we're going to see this get significantly smaller. And the amount by which the input resistance goes up and the output resistance goes down is called the amount of feedback. Not particularly important for this class. We'll get into that in probably more detail than you'd ever care to have in our later classes. Okay. So these are our 5 quantities, many of which we cannot classify for our nonlinear operation circuits. Okay. All right. So as I mentioned at the beginning of class, we are going to analyze this circuit using our practical op amp model. This is absolutely the hard way to do this. And then we are going to introduce our ideal op amp constraints. Okay. So I'm going to start with my practical op amp model. And I'm going to do something here that I'm going to explain. Should be pretty easy and straightforward. But I'm going to say that the voltage on top of my resistor Rn, which has a value of 1 mega ohm, is the inverting input terminal. And the voltage on bottom is the non-inverting input terminal. So I'm flipping that resistance, okay? That does not change the fact that our differential voltage VD is defined to be the voltage at the non-inverting input terminal minus the voltage at the inverting input terminal. I am flipping this resistor over only to make this circuit easier to draw to include the feedback, okay? I'm going to have 10 to the 5 VD here. I have my output resistance, which has a value of 100 ohms here. And if I am not mistaken, I have successfully drawn my practical op-amp model. Now I just have to connect the external connections, right? So are we all okay with this, where this would be totally normal, except for the fact that I've flipped this resistor over. So I put VD on bottom, or excuse me, V plus on bottom, V minus on top. All right, so my non-inverting input terminal is connected directly to ground. So I'm going to accomplish that by simply connecting a wire straight to ground. Between my inverting input terminal and ground, I see that resistor R1 in series with my input voltage. So that's going to look like 5 kilo ohm resistor here. And then a 1 volt source here. And I think the only thing I'm missing now is to label my output voltage and apply my feedback. So my output voltage is the open circuit voltage measured with respect to ground at the output pin. And then my feedback is applied from the inverting input terminal to the output terminal. So like so, where this is a 10 kilo ohm resistor. Are we okay with this redrawing of the circuit? Anything seems suspicious? All right, so what we are going to do now is we are going to apply Kirchhoff's current law at our inverting input node and at our output node to develop a system of equations that we can solve for V minus and V out. So I'm going to add this current, and this current together. And as a second step, I'm going to add this current and this current together. And that should allow me to calculate those two nodal voltages. Okay. So if we apply KCL at the inverting input node, we get V minus minus 1 volt over 5 kilo ohms plus V minus minus V plus, but in this case, V plus is just ground. So just V minus minus 0 over 1 mega ohm plus V minus minus V out over 10 kilo ohms is equal to 0. So based on my drawing, my current or my KCL equation at my inverting input node should have 3 terms, and it does. So I feel pretty strongly that I'm done. Right. Next, we will apply KCL at my output node. And so that's going to be V out minus V minus over 10 kilo ohms. And then I'm going to have V out minus AV 10 to the 5 times VD. So here's where we have to do a little bit of thinking. All right. VD, by definition, is the voltage measured at my non-inverting input terminal, which is 0 volts, minus the voltage measured at my inverting input terminal, which is the nodal voltage V minus. So VD in this case is simply negative V minus. Are we all okay with that? All right. So if I put V minus here, that changes that sign to positive. And then I divide this by my 100 ohm resistor and set it equal to 0. So I now have a simple system, 2 equations, 2 unknowns that I can solve. And in doing so, I will find out that V minus is equal to 20.199 microvolts, very, very small number. And I get V out to be negative 1.9999392 volts. So extraordinarily close to -2. All right. So I have answered part A. We've determined our output voltage. Our analysis gives us something very, very close to -2. Connor, what's up?
I apologize, I'm just having a hard time following. You said VD is equal to negative V minus?
That's correct.
Okay, I'll just have.
No, let's look at it, okay? Our differential voltage VD is always the difference between the inverting input node, the non-inverting input node minus the inverting input node. The non-inverting input node is at ground. So VD is 0 minus this, which is just negative that. Taj. So it should be, it's this voltage minus this voltage with respect to ground, which is exactly 1 volt, because the positive polarity is on top and the negative polarity is on bottom. It would be V minus plus 1 volt if this guy were flipped over. Oh, not at all. Anything else? All right, I'm going to move this before I trip over it and break my old man hip. Okay, so now let's talk about our closed loop voltage gain. Okay. So our closed loop voltage gain, AVCL, is simply the ratio of our closed loop output voltage V out divided by the input voltage that we have applied, which is why I chose a 1 volt source as my input. So this is simply negative 1.9999392 volts per volt. Our closed loop voltage gain here is significantly smaller by several orders of magnitude than our open loop voltage gain. It is not a coincidence that it is related to the ratio of these 2 resistors, which we will discuss more formally in a little bit. Our differential voltage, VD, is negative V minus, or negative 20.199 microvolts. Bradley.
I'm going to ask you, you a system of 2 equations.
So our differential voltage here, which is serving as the input to the op amp portion, is incredibly small, okay? That is because our output is being subtracted from that input voltage that we are applying. This is what we should expect to see with negative feedback, is a very, very small differential voltage, okay? And it also makes sense that we should have an extremely small differential voltage because we're seeing that our output voltage is actually bounded. It's going to fall between VCC plus and VCC minus, at least if VCC plus and VCC minus are in magnitude greater than 2 volts here. So this is another consequence of our negative feedback configuration. These are the 3 straightforward parts, all right? Now let's talk about that input resistance, lowercase r, and output resistance, lowercase r, okay? So for my input resistance, I'm going to define something, okay? Actually, let's do it down here. So this input resistance Rn will by definition be the voltage Vn divided by a current In, where In is the DC current that's leaving the positive polarity terminal of our input voltage source. Okay. So how could we go about figuring out that quantity In? Too difficult. There's a more obvious answer. We know this voltage V minus. So In is simply 1 volt minus this divided by 5 kiloohms. Oh, right? Ohm's law. Why make it harder than it needs to be? So this is going to look like 1 volt divided by 1 volt minus 20.199 microvolts divided by 5 kiloohms is 5,000.100997 ohms, or effectively 5 kiloohms. Okay. So whenever we have a negative feedback configuration and we are applying our input signal through a resistor to the inverting input, we will find that our input resistance seen by our input voltage source is effectively this resistor, okay? If we were applying our input signal to the non-inverting input terminal, we would see a scaled version of this capital Rn value that's scaled by the amount of feedback, okay? So effectively, looking in this way, we see this resistor in parallel with an astronomically huge resistance, which looks like this one. If we look in from this direction, we just see this resistance directly, or a scaled version of it, okay? I'm mentioning this because you're going to have homework assignments, and I want you to understand why there's such a vast disparity between the input resistance when we have an amplifier like this, which is in a inverting configuration, and an amplifier in a non-inverting configuration. Okay. All right. Yes.
With these practical configurations, can you not consider that the current's not going to flow basically through that 1 megaohm resistor? That's like idealized op-amp behavior where that current doesn't flow.
Right. So in this particular instance, we did include it. It's this contribution right here. If we ignored it, which is what we will start doing when we deal with an idealized case, as you suggested, we'll find that this quantity V minus is exactly 0, and this output voltage is exactly -2.
At that point, my question was, why don't we consider that resistor in that out in the feedback loop in series with the voltage? We haven't made that assumption.
Yeah, so that 100 ohm resistance is showing up right here. Why we don't include it in the idealized case, I'll talk about in 5-ish minutes. Yeah, we're getting there. It's about to stop being awful. We just have to understand why we get to do it, because I'm a jerk and I want you to understand why we get to do it. All right. So our last quantity, our output resistance, this guy is a bit interesting, okay? So fundamentally, our output resistance, I think this is quantity E. Sorry, and this should be lowercase r, is I'm going to call this V out prime over I out prime. Now, we're not actually going to calculate it this way, but I want to explain exactly what I mean by this, okay? So in truth, let me use a color I haven't yet used, so purple, okay? So whenever we're calculating the output resistance, what we would do is we would apply a test voltage source at the output, which I'm going to call V out prime. We would determine a current flowing out of the positive polarity terminal, which I'm going to call I out prime. And the ratio of these two quantities is the output resistance seen looking in. This is a Thevenin resistance related calculation, which means we have to short out our input signal, okay? Now, the reason why we're not going to calculate this quantity in this way for this very specific instance is because we know that the Thevenin resistance is nothing more than the Thevenin voltage or open circuit voltage divided by the Thevenin current, or excuse me, Norton current, or the short circuit current. The V out that we calculated at the beginning is the Thevenin voltage for this circuit. So we don't need to do that work again because it was already told to us. The only thing we need to do now is to reanalyze this circuit with the output terminals shorted to get I Norton, and that gives us an alternative way to calculate our output resistance lowercase r. Okay, so we were applying Thevenin's theorem here to calculate the resistance seen looking into the output terminals using the Thevenin voltage divided by the Norton current, which will get us literally the exact same results as if we had applied a test source of a fixed voltage and measured the test current, which I proved to the overwhelming majority of you guys in circuits 1 on multiple different occasions. So this is the same thing as V Thevenin over I Norton, okay? We know that V Thevenin is 1.9999392 volts because we have already calculated the open circuit voltage for this circuit, okay? So that part's taken care of. Now we have to circle back around to determining the Norton current, okay? So to determine our Norton current, I'm going to redraw our circuit here. I'm going to do this fairly quickly. the change that I am going to make is my 1 volt source. So this is our original circuit. I am now simply going to short the output terminals and measure that short circuit or Norton current. Okay. That actually greatly simplifies things. Right? What I mean by that is I now know effectively that my output voltage for this guy should be 0. So I only need to write a KCL equation at this node. And then I can once I know the quantity V minus, I can simply apply Kirchhoff's current law here to determine I Norton. Okay. So if we apply KCL at our inverting input node, we get V minus minus 1 volt over 5 kilo ohms plus V minus over 1 mega ohm plus V minus over 10 kilo ohms is equal to 0. Solving that one equation, one unknown system, if you can even call it that. I get V minus to be 0.6. Sorry, my stylus is being odd. 66445 volts. From this, I Norton is V minus over 10 kilo ohms plus 10 to the 5 times VD. So negative 10 to the 5 V minus divided by 100 ohms, which comes out to be negative 664.45176 amperes. I want to explain something here that should be obvious, but maybe isn't. Okay. If I physically short-circuited the output terminals of an op-amp, I sure as hell am not going to see that op-amp carry 665 amps of current because it'll burn it the hell out real quick, right? So this is a theoretical calculation using the practical op-amp model parameters. We would never actually see this amount of current carried by a single op-amp, okay? Now, if we plug that number in, here, we find that our output resistance, lowercase r for our op-amp, is roughly 3 milliohms. So this is leading us into our discussion on ideal op-amps, but I want to look at a couple of things that we have observed here in the analysis of this problem for a practical op-amp circuit, okay? Our output resistance of 3 milliohms is very, very small, close to 0. Our input resistance of 5 kiloohms is extraordinarily close to this, which means effectively everything to the right of that resistor looks like an open circuit. All right. And our differential voltage VD is very, very small. Okay, so those are 3 observations that we made in the analysis of this practical op-amp model circuit that contains negative feedback. Now we are going to discuss what the actual ideal parameters are. Okay. So oops. What we are developing here is only applicable to negative feedback circuits, okay? So let's look at the generic amplifier case that we talked about way at the beginning of this section of class. Where we have a practical voltage source applying a signal that is placed at the input of an amplifier, which we are defining using our ideal op-amp model, or excuse me, our practical model. All right, so just to break things down again real quick, like here in the middle, we have our amplifier model. On the left-hand side, we have our source. And on the right-hand side, we have our load. And we determined previously that ideally, the voltage drop across our load, VL of t, would be simply a scaled version of our signal voltage, Vs of t, that was applied at the input terminals of our amplifier, okay? What we're going to do now is figure out what parameters make that statement exactly true, okay? Or as close as to it as we can get. So, in order for us to make this statement to be true, 2 things must occur. Let's talk about the first. Our first condition is that all of this voltage Vs is applied across our input resistance. Okay? So effectively right now, we have a voltage divider circuit, and we want to see all of this voltage show up here. What value of Rn makes that happen? Extremely high or infinitely large. So if Rn were an open circuit, no current could flow through Rs, which means all of Vs shows up here. Absolutely right. So our first parameter is that Rn needs to be infinity ohms in an ideal case. All right. Now, with this satisfied, all of our input signal is Vs of t. And so our voltage here is AV times Vs of t. How do we make sure that all of that voltage gets applied across our output terms? Because again, we have another voltage divider. What does R out have to be to make all of this voltage appear here, which in turn appears here? 0. My thing will write. So for an ideal amplifier, R out is exactly 0. The last piece of this, unfortunately, cannot be determined by this model. It is simply for an ideal amplifier, it will have a gain that is infinitely large, which means it is extraordinarily well controlled by feedback. So these are our ideal op-amp parameters. We are going to reanalyze that same circuit using these ideal op-amp parameters, make a couple of observations that will exactly lead us into our rules for ideal op-amp circuits, as we discussed in circuits 1. All right, so our example revisited. We have an infinity ohm resistor here. This is still V plus, this is still V minus. We have ground here. We have infinity times VD here. Let's see, plus minus VD. We have a 0 ohm resistor here. Here is our output voltage. The out. Here is our 5 kilo ohm resistor. Here is our 1 volt source. Here is our 10 kilo ohm feedback resistor. And there's ground. Okay. All right, so let's begin our analysis with an observation. Since this is a 0 ohm resistor here, or a short circuit, V out is exactly equal to infinity times VD. Are we okay with that? So if V out is infinity times VD, then that means that VD is V out over infinity, or 0 volts. This is where our voltage constraint equation comes from. Our differential voltage must be 0 volts in an ideal op-amp, which means the voltage here V plus and the voltage here V minus must be the same voltage. So this is where one of our ideal op-amp rules comes from. Okay. Now, we can apply Kirchhoff's current law at our inverting input node and find, so this is KCL at V minus, that V minus minus 1 volt over 5 kilo ohms plus V minus minus V out over 10 kiloohms plus V minus over infinity ohms is equal to 0. Well, that V minus over infinity bit obviously contributes 0 amps. And this tells us that no current can flow into or out of the input terminals of our ideal op amp. So that's where our second ideal op amp rule comes from. Okay. So we now have this simple equation, which using a very trivial amount of algebra tells us that V out is negative 10 kiloohms over 5 kiloohms times 1 volt, or 2 volts. Where we can explicitly see here that our closed loop gain is purely a function of the resistor network that we've applied to our circuit. So, as a closing remark here, we have now demonstrated why, very specifically, for negative feedback circuits, number one, V plus has to be identical to V minus, which means there can be no potential difference between the input terminals of an ideal op amp and number two, since Rn is infinitely large, there can be no current flowing into or out of the input terminals of an ideal op amp. All right, I think that is enough out of me for today. So our plan for Monday is we are going to review those negative feedback commonly used op amp topologies. So we're going to talk about inverting amplifiers, non-inverting amplifiers, buffer amplifiers, differentiators, integrators, inverting summers, differencing amplifiers, all that kind of good stuff. All those amplifiers that we didn't really need to know the names of and understand because we could just apply our simple op amp rules in circuits 1, we are going to use as building blocks in our design projects. So we kind of need to know what they are and understand how they work.